Welcome to Lecture 31, in which I want to talk about the energy that's stored in distributions of point charges, so-called electrostatic systems. Why would we be interested in that? Well, let me give you two important reasons. First of all, if you think of any molecule, that molecule is ultimately a distribution of electric charge. That distribution stores energy, and the energy that's stored, for example, in things like fossil fuels, gasoline, oil, natural gas, coal, this is the energy associated with molecular distributions of electric charge. And consequently, most of the energy we run the world on is really electrostatic energy being released as we reconfigure these molecules. In technology, we use electrostatic energy in a wide variety of situations, from simple camera flashes to enormous devices that have to release a lot of energy in a very short time to simulate nuclear explosions, to the defibrillators that we use to revive cardiac victims, for example. All these use stored electrostatic energy released very quickly. So let's take a look at energy stored in electrostatic systems. Here I have a couple of point charges, my red balls representing point charges, and I'm simply going to imagine starting with them fairly far apart and then beginning to bring them closer and closer together. Now that takes work, because there's a repulsive electric force between them, or equivalently, each one creates an electric field at the location of the other. So as I bring them together, first I have to do a little bit of work, but then it gets harder and harder because that force gets stronger and stronger. Oh, very difficult. Oh, I've done a lot of work. But the electric force is conservative, meaning that that work gets stored as potential energy. And if I were to release these balls, they would go flying apart under the influence of that repulsive force. But if I somehow held them in place, somehow glued them together close by each other, I would have stored that energy that I put in as work when I moved them close together. That would be the stored electrical energy. And we want to look at that energy, and we want to understand it in both molecular systems and ultimately technological systems. So let's begin looking at what happens as we try to do the simplest thing we could imagine here, bring a few point charges together just as I did here. So let's do that. So this picture shows a point charge and its electric field, something we're quite familiar with now. We developed the point charge potential in Lecture 30. We developed it as the work per unit charge it takes to move from infinity to a distance r from a point charge q. So here I show a point charge q1 sitting there with its electric field, and I'm going to imagine bringing a second point charge q2 from very far away, essentially infinitely far, to the vicinity of point charge q1. So here it comes. In it comes, and it ends up a distance r from point charge q1. And we know from the preceding lecture that the potential at point r, that is the work per unit charge to come in from infinity to that point, is kq1 over r. That's the work per unit charge. Now we've brought in a charge q2. If it were 1 coulomb, the work would be kq1 over r, but it's kq1 over r times however many coulombs there are in q2. The work to bring q2 in is kq1 over r. That's the potential at that point, the work per unit charge, times the charge q2 that we brought in. Now, because the electric force is conservative, that work that we did ends up being stored as electrostatic potential energy. So the stored potential energy of a system of 2 point charges is kq1, q2 over r. And in this case, just like when I brought my red balls together, that energy is a positive stored energy because I had to do work to bring those two charges together. What if the charges were opposite? Well, here I've got exactly the same situation, except I've got a negative charge far away. It's going to feel an attractive force, and work is going to be done on that charge. Equally, I would have had to sort of hold the charge back with a force the other way if I didn't want it to fall toward the positive charge. So here in it comes. It ends up a distance r from the point charge also, and exactly the same formula applies, except now I have two opposite charges, q1 and q2, and consequently I've got a negative stored potential energy. Now what does negative energy mean? It simply means this. It means if I wanted to remove those two charges to a very large distance, I would have to do work equal to the negative energy that's involved here, but a positive amount of work of the same magnitude. So there's nothing mysterious or funny about negative energy. Negative potential energies generally describe a system where two things are bound together by an attractive force, and that is certainly true, for example, of molecules, as we'll see in a minute. So now the energy is negative. U represents the work it would take to separate those charges. So let's do an example of that, where we look specifically at the energy involved in, say, assembling something real like a molecule. So let's move over to our big screen where we do quantitative things and do a quantitative thing. Okay, so let's look at how we might make water. Here's a water molecule, H2O, 2 hydrogens and an oxygen make up the water molecule, and we want to apply what we know about the electrostatic energy of point charges to figure out what energy is involved in making this water molecule. We know that the energy of 2 point charges is K, Q1, Q2 over R, where Q1 and Q2 are the 2 point charges. So let's take this water molecule now and look at it as an assemblage of point charges. Now, this picture I'm showing you is not exactly correct. It isn't quite as simple as that. I've indicated that the oxygen has -2 elementary charges and the 2 protons each have, the 2 hydrogens each have +1 charge. That's because the electrons from the hydrogens tend to get wrapped up around the oxygen, but not exactly. So these numbers are a little bit larger than the actual effective charges, but we'll work with that. And we know for the water molecule that the spacing between the hydrogen and oxygen center to center is approximately 1/10 of a nanometer being 1/1000th of a meter. And we know that the distance between the 2 hydrogens is about 0.16 nanometers. So now we're ready to compute the energy that was involved in putting this system together. Let's start with the oxygen in place, and let's think about bringing one of those hydrogens in from infinity, essentially. So we just did that problem. That's the case of a positive charge and a negative charge. The answer is KQ1, Q2 over R. It's K. Q1 is the -2e of the oxygen. Q2 is the positive e of a proton, the positive part of the hydrogen, divided by this distance RHO. So we've brought one of the hydrogens in. There's the work involved. I'll call that W1. Next, we're going to bring in the second hydrogen, and then we'll have the molecule all put together. We simplify that a little bit. It's 2K squared, Ke squared over RHO. Now we'll bring in the second hydrogen. Well, we got to bring in the second hydrogen in the electric field of the oxygen. Well, that's the same as before. It's -2Ke squared over R hydrogen to oxygen. That's the same as bringing in the first one in the electric field of the oxygen that was there. But now we got something else going on because we've got the other hydrogen. The first hydrogen is already there, and it provides a repulsive force on the one we're bringing in, and so we have to do positive work against that one. And so the total work is the sum of those two terms, -2Ke squared over the distance between the hydrogen and oxygen, plus Ke squared, K this E times this E, divided by that distance squared, RHH. That was the work to bring in the second hydrogen. The total work it took to build the whole molecule is the sum of those two, and that's the work that gets stored as electrostatic energy in the water molecule. So there it is. And we know we can simplify it a little bit, just factor out the Ke squared that's common to them, and we have a positive term and a negative term. The negative term is bigger, and so the energy is negative, which tells us we have a bound molecule. We know the numbers. We know K, we know E, we know these things, these numbers. Work it out. You get an energy of about -8 times 10 to the -19 joules. Now, because of the approximation I made in this simple model, that actually is off by a factor of about 4, but that's not bad. With this simple calculation based on some very simple things we know about electric charges, we've been able to estimate the energy that was released, if you will, when the water molecule was formed, or equivalently, the energy we would have to take apart to make a water molecule. But importantly, if we burned hydrogen and oxygen, use them as fuels, we would release this much energy as we form a water molecule. I just happened to do a simple calculation. In a cup of water, if you look up the actual value, which is about a quarter of this, a cup of water it took about, you released about -2 kilowatt, you released about 2 kilowatt hours when you made a cup of water. By the way, a gallon of gasoline contains about 40 kilowatt hours of energy by comparison. To make a cup of water, about 2 kilowatt hours of energy were released. You would have to supply about 2 kilowatt hours to take the water apart. So there's an example, making water, where we actually calculated something pretty profound, the energy involved in forming water, from very simple first principle considerations of point charges. Okay, that was an example of electrostatic energy stored in a natural system, in that case the water molecule. Let's now turn to technology and look at how we use energy storage in technological devices. Here's a model of a system that can do that. This is a pair of parallel metal plates. They're quite broad in area compared to the relatively narrow spacing between them, and they constitute what's called a capacitor. And I want to talk a bit more about capacitors because they are our primary technological energy storage device. This combination is called a parallel plate capacitor. It would be rare to see an actual capacitor this big or this widely spaced. Capacitors are made much smaller, and I'll show you some shortly. But I'm going to work on this model as an example of showing you how parallel plate capacitors work, how capacitors work in general, and ultimately how much energy they store. And then we'll swing back into some more profound look at energy storage in capacitors. So let's look at this idea of capacitors and their measure of their, quote, capacitance, how much charge, in some sense, they can hold. So here's a picture of a parallel plate capacitor, like I just showed you, a pair of conducting plates. They have area A. They have a spacing between them, D. I'm going to put charge Q on one plate, plus Q, and charge minus Q on the other plate. So a capacitor stays electrically neutral, but you put charge on one plate and the opposite charge on the other, and these conducting plates. There's going to develop an electric field in that region, and if the plates are parallel and quite closely spaced, that field will be essentially uniform, and so it's easy to work with. There will be, as a result of that electric field, a potential difference, because we know there are potential differences, because you have to do work moving against that field. So the potential difference is V, and I'm going to define the capacitance as the ratio of the charge plus Q or minus Q, just the magnitude of that charge Q divided by the voltage. So the more charge you can put on there for a given voltage you put between the plates, the bigger its capacitance. That ratio has the units of coulombs, charge, per volt, voltage, and that unit defines what's called a farad. 1 farad is a rather, actually, very large capacitance. Capacitances can be measured down to microfarads and even picofarads, 10 to the minus 12 farads, although there are 1 farad and bigger capacitors available also. So that's just a quick introduction to a parallel plate capacitor and capacitance. Let me try to motivate for you what the capacitance of a parallel plate capacitor is. The bigger the area of these plates, the more charge I could put on them for a given voltage, and consequently I'd expect the capacitance to depend on the area, to scale linearly with the area. Double the area, you double the capacitance. On the other hand, if you separate these plates farther, for a given charge, you get a greater voltage for a given charge and field, because if you separate the plates, the electric field stays essentially the same for a given charge, but now it's over a bigger distance, so the voltage is bigger, and so the capacitance Q over V goes down. And so the capacitance ought to be proportional to 1 over the distance, inversely proportional to that separation distance. And so capacitance scales as A over D, and in fact, without deriving it mathematically, it's A over D with a constant, and the constant, not surprisingly, involves that electrical constant, the Coulomb constant K. So that's capacitance scaling as a function of area and D, distance separation. There's also a question of what you put in between the plates to insulate them. My parallel plate capacitor with 2 big metal plates had air, but often we put an insulating material between them, partly to keep the plates apart, but more importantly also to change the capacitance. And we can think of insulating materials. They don't conduct, but they consist of little dipoles. Molecules are dipoles. And those dipoles flip and align themselves with the field. So the molecules act as dipoles in this insulating material. They align themselves with the electric field, which I'll call E sub 0, the electric field created by the charge on the capacitor. And the dipole's field, when they align, if you look at this little picture, ends up being opposite the field that was applied, because the negative part of the dipole is going to be attracted to the positive plate. So the dipole's field goes the other way, and that reduces the overall electric field in the capacitor. That, in turn, lowers the voltage for a given charge, and that gives you a greater capacitance. So that's the role of insulation in capacitors. So real capacitors have insulation, and it serves to increase the capacitance. Let's look at some capacitors and see what we can do with them. So over here I have some examples of real capacitors. These are large capacitors that actually are called electrolytic capacitors, and the insulation is formed by chemistry that occurs when you apply a voltage across them. These have capacitances in the range, this is the biggest one, of about 18 millifarads, 18 thousandths of a farad. It's actually listed as 18,000 microfarads, but that's the same thing. And these are mostly decreasing in capacitance. That one's about 100 microfarads, about 10 microfarads. And the final ones down here have capacitances that are measured in picofarads, on the order of 10 to the minus 12 farads. Capacitors are used widely throughout electronics and electricity, and I'll talk more about their applications in a minute. Some of you are probably old enough to remember old-fashioned analog radios where you turned a dial to tune the station. What you were doing then was turning the shaft of a variable capacitor. This structure has parallel plates that, as their configuration relative to each other changes, the capacitance of that system changes. So there are some examples of real capacitors. Now, these capacitors we're talking about are not only storing electric charge, they're also storing energy because they are systems of charges, electrostatic systems, and so they have energy involved. And I would like to talk about that energy and show you exactly how much energy is stored in a capacitor. So let's go over to our big screen and look at the energy stored in a capacitor. We'll start with a capacitor with no charge on its plates, so there's no potential difference between them. There's no electric field. We'll move a little bit of charge from the bottom plate to the top plate, and in so doing, at first we won't have to do any work because there's no electric field, but as soon as we get a little bit of charge up on that top plate, we've got to do some work to move more. And as we build up more and more charge, it gets harder and harder to move charge from the bottom plate to the top. Now, we don't actually pick up charge and move it. We connect wires and we flow the charge with sources of electrical energy like batteries, but same idea. So we move a little bit of charge, and eventually, each subsequent move takes more work, and eventually we get the capacitor fully charged, depending on what voltage we're putting across it. That's what defines fully charged, and we got a big electric field, we got a lot of charge. So let's figure out how much energy is involved in doing this. If the voltage were always V, it would take work Q times V to move all the charge, because voltage is work per unit charge or energy per unit charge. But we started with no charge, and we ended up with charge Q. So in fact, the average voltage was V over 2. And so the work to move all that charge was Q times V divided by 2. Now, I'm doing a kind of quick averaging because the buildup happens linearly. This is mathematically correct. We could really do this with calculus, and it wouldn't matter how we did the buildup. But that's the right answer for the work involved. So this is the energy that gets stored in the system because the electric force is conservative. The capacitance, C, is Q over V. So that's the capacitance. I'm going to solve that for the charge. The charge is C times V, and I'm going to put that in here for charge, and I get the stored energy being 1/2 CV squared. That's the energy stored in a capacitor. So capacitors store energy. The energy is equal to 1/2 times the capacitance times the square of the voltage. The voltage doubles, you get 4 times as much energy. So that means high voltage capacitors are very good energy storage systems. Okay, let's look at some examples of this energy storage in capacitors. I'll begin with a demonstration. Here I have a very large capacitor. It's a large electrolytic capacitor. It's rated at a maximum of 60 volts, so I've got to be a little bit careful about how much voltage I put across it. I have here a power supply that's capable of supplying 50 volts, and I'm going to set that power supply to 50 volts, and I'm going to use it to charge that capacitor. So let me begin by setting the power supply. Okay, so I'm going to connect my capacitor to this power supply. First, I'll turn on my voltmeter so I can record the voltage across the capacitor. It will actually take a little while for it to build up. Okay, so I'm going to apply a voltage here, and we're going to watch that voltage build up gradually. I'll show you later why it's happening gradually. There it is. We're at 30, 40 volts, 43, 45, 46. There we go, building up, and reaching about 50 volts, which is about the maximum it's going to get to because of the settings on my power supply. Okay, once I get there, I'm going to disconnect the power supply, the capacitor from the power supply. The voltage is still there. It'll go down gradually, but it's basically there because the capacitor is storing that energy, and now I'm going to do what capacitors are good at. I'm going to release that energy very suddenly on this beautiful, shiny, new screwdriver. So here I go. The screwdriver is no longer beautiful and shiny and new because it's had a big place where it actually vaporized the steel because of the sudden release of the energy stored in that capacitor, and you'll notice the voltage at the same time has dropped to almost zero. So that's an example of what capacitors can do. They can store energy, and then they can release the energy very quickly. Let me give you some examples of applications in which that happens. Defibrillators, I mentioned before. When you're defibrillating a patient with a heart that's gone into fibrillation, you want to supply a very sudden high-energy jolt of electric current to that heart. It's hard to do that with batteries or other power sources. You'd have to have enormous, massive batteries, but it's relatively easy to charge up a capacitor and then let that energy go very suddenly. In the middle frame frame at the top, you see a mass transit train of the Bay Area Rapid Transit System in the San Francisco Bay Area. As BART trains come into the station, they don't put on frictional brakes to dissipate their energy. Instead, the energy runs an electric generator, which stores energy briefly in a capacitor, so-called ultracapacitor, and as the train accelerates out of the station, it uses that energy, so the total energy consumption of the train becomes much less. On the top right, you see computer memory, which is another example of energy storage in capacitors. By the way, on that little memory strip, there are more individual capacitors, probably 8 billion of them if it's a 1 gigabyte memory strip, and that's more than there are people on the planet, at least right now. At the lower left, you see a camera flash. When a camera flash goes off, it suddenly dumps the energy in a capacitor through the flash bulb of the camera or the flash lamp. It's energy that it would take a long time for a battery to be able to supply. A battery couldn't flash that flash, so we charge a capacitor gradually and then discharge it very suddenly. That's why it takes a while after you take a flash picture before you can take another one. The capacitors shown in the middle of the row of the bottom are capacitors used in giant experiments where we are attempting to duplicate nuclear fusion here on Earth, and we're discharging enormous amounts of energy, so much energy that during the short time they're discharging, the total power may be roughly equal to that of all the world's electric power plants. And finally, a more mundane application for the kinds of capacitors I've showed you already. Capacitors provide smooth power in electronic equipment that needs steady direct current power, whereas the power line supplies us with alternating current. So there are some applications of capacitors, some technology. Well, now let's go from technology back to philosophy and talk about something very deep that we'll get out of these capacitors, something that will give this whole field concept more reality than it had before. And let me begin by doing a calculation here on our onset monitor. So let's go deeper. We know that the energy stored in a capacitor is a half CV squared. Here's a picture of a charged capacitor. It's got an electric field in it, and I want to work on this expression a little bit to give you some deep insights into stored electrical energy. We know the voltage between the plates is the electric field times the spacing. It's essentially a uniform field. We've seen that before. We defined voltage or potential difference as the product of field and separation, in that case E and D. Capacitance is Q over V, and we found out earlier for a parallel plate capacitor, that's the area divided by some constant, 4 pi times the Coulomb constant, and D down there. So let's rewrite the stored energy. It's a half CV squared. Here's my C, A over 4 pi KD, so there's C. Here's V. V is E times D, so it's E squared times D squared. And let me work on that a little bit. That is A times D. We got 1D downstairs, canceling one of the D's upstairs. So we got 1D left upstairs. We got the E squared, and we got 2 and 4, and that's 8 pi K. Well, this is a lot of math. Why is this going to give us a deep insight? Well, here's why. Let's group that a little bit differently. Let's group that as some constant. Constants aren't really super important, but they're there, and in this case, it's the electrical constant modified a little bit. We have the square of the electric field, and then we have the product of the area with that distance. And let me get a little bit more profound now about what's happening with that result. Let's switch to a regular visual and see if we can understand that result a little bit more. So here's our result for the energy stored in a capacitor. It's this constant times the square of the electric field times the separation of the plates multiplied by their area. There's the constant, there's the square of the electric field, and what is that separation multiplied by that area? It's the volume inside the capacitor. It's the area of this rectangular region times the height of that rectangular region. So if we really want to think about this profoundly, we look at that quantity and we say that is the density at which energy is stored in that electric field. In this particular case, we multiply that density, joules per cubic meter, energy per volume, by the volume, and we get the total energy stored in the capacitor. Now, this is not a proof, but it is in fact a motivation of the fact that anytime there is an electric field anywhere in the universe, it represents stored energy, and the stored energy density, the energy per unit volume, right at that point where the electric field has strength E, is proportional to E squared. So if you double the electric field, you quadruple the energy density. I haven't proved that. If you take an advanced undergraduate electromagnetism course, we go through a lot of calculus, and we rigorously prove that that's true for any electric field. But that is a profound statement because that statement tells us now that electric fields really have substance to them. This is not just a mathematical artifact we've kind of introduced to talk in highfalutin terms about fields. The field is a repository of stored energy. Anywhere there's an electric field, there is electric energy density proportional to E squared given by that amount. So that is really a profound result. And let's do one more example to show you what that result means. So let's go to our big monitor again, and let's talk about energy storage in electric fields. And let me pose the following question. Could you possibly store in an air-insulated capacitor energy with the same energy density as the energy density in gasoline, which is also stored electrical energy, but it's stored in those microscopic electric fields of the molecular configurations of the gasoline relative to the carbon dioxide and water you would make if you burned the gasoline? So could you do that? Could we use capacitors to power our cars? Why don't we just fill our cars with capacitors, charge them up, and drive away? So the question is, could we store energy in an air-insulated capacitor with the same density as gasoline? So a gallon of gasoline happens to be about 4/1000ths of a cubic meter, because a cubic meter is pretty big. So the density in gasoline is 0.1 gigajoules, 0.1 billion joules, 100 million joules in a gallon. That ends up 25 million joules, if we do the math here, in a cubic meter. So the energy density of gasoline is about 25 gigajoules, 25 billion joules per cubic meter. The electric energy density we found is E squared over 8 pi k. It's what was in the capacitor without the term involving the capacitor's volume. Let's equate those two and let's solve for E. So we're going to equate the energy density in the electric field with the energy density we found for gasoline. And let's solve it for E, work the numbers, take the square root, and we get 8 times 10 to the 10 volts per meter, 8 times 10 to the 10 newtons per coulomb, 80 billion volts per meter. Well, remember the breakdown field in air, the field at which air breaks down and becomes a conductor, sparks go flying, and a capacitor's insulation, air, ceases to be insulation. That's 3 million volts per meter. This is 80 billion volts per meter. Absolutely no way are we going to do that. We cannot store energy in capacitors, especially air-insulated capacitors, but really in no capacitor because these are so different, with anything like the energy density of gasoline. So we aren't going to use capacitors as the primary storage motive for cars. It doesn't mean we can't temporarily store energy in capacitors, as was done in that subway system in the Bay Area, where for a brief few minutes we store a little bit of the train's energy. The kinetic energy it had as it was slowing gets stored as energy in the capacitors and then is used up again as the train starts up again. But most of the train's motive comes from power plants. So this is a deep, profound idea that electric fields all represent stored energy. So let's summarize Lecture 31. We found that every arrangement of electric charge, whether it's something we build technologically or something nature builds in a molecule, represents stored electrostatic energy. That energy may be positive if we put like charges together and repulsive forces are dominant. It may be negative if we have attractive forces dominating, and then we get bound structures like molecules. We developed a technological application of this in the form of capacitors, which store charge in two oppositely charged conductors. They also store energy as well as charge. And then we went from capacitors, a relatively mundane technological idea, to this very deep, profound idea that all electric fields everywhere in the universe are repositories of stored energy, an idea that gives the electric fields a new reality that they didn't really have for us before. And finally, we know that the density of the energy stored in electric fields, we worked that out mathematically, depends on the square of the electric field strength.